Hey, Kristen, how's it tracking?
With Carvana Value Tracker?
What else?
Oh, it's tracking. In fact, Value Surge Alert trucks up 2.5%. Vans down 1.7.
Just as predicted. So, we gonna...
I don't know. Could sell, could hold.
The power to always know our car's worth.
Exhilarating, isn't it?
Tracking.
Always know your car's worth with Carvana Value Tracker.
Of course. Here's a script for a YouTube video on partial differential equations, PDEs. Introduction. Opening shot of mathematical symbols and equations on a blackboard. Host, voiceover. Hello everyone, and welcome back to your channel name. In today's video, we're going to delve into a fascinating topic that's essential in the world of mathematics and science: partial differential equations. Camera transitions to the host standing in front of a whiteboard. Host, on screen. Partial differential equations, or PDEs, are a powerful tool for modeling physical phenomena and solving complex problems. By the end of this video, you'll have a good grasp of what PDEs are and why they're so important. What are partial differential equations? Visual aids and equations appear on the whiteboard as the host explains. Host, voiceover. So, what exactly are partial differential equations? In essence, they are equations that involve partial derivatives of a multivariable function. Camera zooms in on equations. Host, on screen. Here's a general form of a partial differential equation. Equation appears on screen. Host, voiceover. ut plus qx equals 0. Host, on screen. In this equation, u is the function we're trying to find, t and x are independent variables, and c is a constant. Camera transitions back to the host. Host, on screen. Now, let's understand why PDEs are so important. Importance of partial differential equations. The host discusses the significance and applications of PDEs. Host, voiceover. Partial differential equations are a cornerstone of mathematical modeling. They are used to describe a wide range of phenomena in fields such as physics, engineering, biology, and economics. Real-world examples and diagrams illustrate applications. Host, voiceover. Whether it's modeling heat transfer in a solid, simulating fluid flow, or predicting stock market trends, PDEs provide the mathematical framework to understand and solve these complex problems. Solving partial differential equations. The host explains the general approach to solving PDEs. Host, voiceover. Solving PDEs can be quite challenging, but there are several methods and techniques available depending on the type of PDE you're dealing with. 1. Classification of PDEs. Host, on screen. The first step is to classify the PDE. Is it linear or nonlinear? Is it first order or higher order? 2. Choosing an appropriate method. Host, on screen. Next, choose an appropriate method. You might use separation of variables, the method of characteristics, or numerical methods like finite differences or finite elements. 3. Applying boundary and initial conditions. Host, on screen. Always remember to apply boundary and initial conditions to find the specific solution that fits your problem. Camera transitions back to the host. Host, on screen. In summary, partial differential equations are a vital mathematical tool with widespread applications. We've learned what they are, why they matter, and the general approach to solving them. Conclusion. Host summarizes the key points. Host, on screen. I hope you found this video informative and inspiring. If you did, please give it a thumbs up and subscribe for more educational content. And if you have any questions or topics you'd like to see in future videos, please leave them in the comments below. Outro music fades in. Host, on screen. Thank you for watching, and remember, partial differential equations are the language of the universe, helping us unlock the mysteries of our world. Stay curious, and keep exploring the world of mathematics and science. Introduction. Opening shot of a chalkboard with equations written on it. Host, voiceover. Greetings, math enthusiasts. Welcome back to your channel name. In today's video, we're going to dive into a fascinating technique for solving differential equations, using series. Camera transitions to the host standing in front of a whiteboard. Host, on screen. Solving differential equations using series might sound complex, but fear not. By the end of this video, you'll have a solid understanding of this powerful method. Understanding series solutions. Visual aids and equations appear on the whiteboard as the host explains. Host, voiceover. So, what exactly are series solutions and why are they useful? Well, in some cases, we can't find an explicit algebraic solution to a differential equation. That's where power series come to the rescue. Camera zooms in on equations. Host, on screen. A power series is an infinite sum of terms involving powers of x. Equation appears on screen. Host, voiceover, fx, equals, n equals 0, nxn. Host, on screen in this series, n are constants, and x is the variable. Now let's see how we can use series to solve differential equations. Solving differential equations with series. The host explains the steps as equations, and graphs are displayed. Host, voiceover, to solve a differential equation using series, we'll follow these steps. 1. Start with the differential equation. Host, on screen, begin with the given differential equation. 2. Assume a series solution. Host, on screen, assume that the solution can be represented as a power series. 3. Find the derivatives. Host, on screen, differentiate the series to find its derivatives. 4. Substitute into the differential equation. Host, on screen, substitute the series and its derivatives into the differential equation. 5. Solve for the coefficients. Host, on screen. This will give you a recurrence relation for the coefficients n. Solve this relation to find n. 6. Construct the series solution. Host, on screen, use the found coefficients n to construct the series solution. Camera transitions back to the host. Host, on screen. And there you have it. A series solution to a differential equation. Applications. The host discusses real-world applications of series solutions to differential equations. Host, voiceover, series solutions are incredibly powerful and versatile. They are used in physics, engineering, and many other fields to solve differential equations that describe complex phenomena like heat conduction, quantum mechanics, and more. Conclusion. Host summarizes the key points. Host, on screen. In conclusion, solving differential equations using series is a valuable technique when traditional algebraic methods fall short. We've learned what series solutions are, how to use them, and their real-world applications. Closing shot of the host in front of the whiteboard. Host, voiceover. I hope you found this video informative and inspiring. If you did, please give it a thumbs up and subscribe for more educational content. And as always, if you have questions or suggestions, feel free to drop them in the comments below. Outro music fades in. Host, on screen, thank you for watching, and remember, series solutions are like mathematical tools that unlock the secrets of the universe. Stay curious, and keep exploring the wonders of mathematics. Introduction. Opening shot of a chalkboard with equations written on it. Host, voiceover, hello, everyone, and welcome back to your channel name. Today, we're going to tackle a fundamental concept in differential equations, the initial value problem. Camera transitions to the host standing in front of a whiteboard. Host, on screen. In this video, we'll explore what an initial value problem is, how it's defined, and why it's essential in understanding the behavior of dynamic systems. What is an initial value problem? Visual aids and equations appear on the whiteboard as the host explains. Host, voiceover. So, what exactly is an initial value problem? At its core, it's a type of differential equation problem that involves finding a solution to an equation while specifying the initial conditions of the system. Camera zooms in on equations. Host, on screen. Mathematically, an initial value problem typically looks like this. Equation appears on screen. Host, voiceover. Di dx equals fx. Y, where y equals b. Host, on screen. In this equation, y represents the function we're trying to find. Fx, y, is a given function, a is the initial x value, and b is the initial y value. Camera transitions back to the host. Host, on screen. Now, let's understand how we can solve initial value problems. Solving initial value problems. The host explains the steps as equations, and graphs are displayed. Host, voiceover. Solving an initial value problem involves finding a function x that satisfies the differential equation and the specified initial conditions. 1. Start with the equation. Host, on screen. Begin with the given differential equation and initial conditions. 2. Integrate and find the general solution. Host, on screen. Integrate the equation to find the general solution. 3. Apply initial conditions. Host, on screen. Now, apply the initial conditions y equals b to determine the specific solution. 4. Obtain the unique solution. Host, on screen. This process results in a unique solution to the initial value problem. Camera transitions back to the host. Host, on screen. And that's how you solve an initial value problem. Applications. The host discusses real-world applications of initial value problems. Host, voiceover. Initial value problems are widely used in science and engineering to model and understand dynamic systems. They help us predict everything from population growth to the behavior of mechanical systems. Conclusion. Host summarizes the key points. Host, on screen. In conclusion, an initial value problem is a fundamental concept in differential equations, enabling us to find solutions while specifying the initial conditions of a system. We've learned what it is, how to solve it, and its significance in various fields. Closing shot of the host in front of the whiteboard. Host, voiceover. I hope you found this video informative and helpful. If you did, please give it a thumbs up and subscribe for more educational content. And if you have any questions or suggestions, feel free to leave them in the comments below. Outro music fades in. Host, on screen. Thank you for watching, and remember, initial value problems are the starting point for understanding dynamic systems. Stay curious, and keep exploring the world of mathematics and science. Introduction. Opening shot of a chalkboard with equations written on it. Host, voiceover. Hello, everyone. Welcome back to your channel name. Today, we're delving into a powerful mathematical tool that has a wide range of applications, the Laplace transform. Camera transitions to the host standing in front of a whiteboard. Host, on screen. In this video, we'll demystify the Laplace transform, explain how it works, and show you how it can be used to solve complex problems in engineering, physics, and more. What is the Laplace transform? Visual aids and equations appear on the whiteboard as the host explains. Host, voiceover. So, what exactly is the Laplace transform? At its core, it's a mathematical technique that transforms a function of time, often denoted as ft, into a function of a complex variable s, typically denoted as f's. Camera zooms in on equations. Host, on screen. The Laplace transform is particularly useful when dealing with linear time invariant systems, as it simplifies the analysis of differential equations. Camera transitions back to the host. Host, on screen. Now, let's dive into how we compute the Laplace transform. Computing the Laplace transform? The host explains the process step by step. Host, voiceover. Computing the Laplace transform involves integrating the product of the function ft and e, street, over all time t. Equations and integral notation appear on the whiteboard. Host, voiceover. Here's the formula for the Laplace transform. Equation appears on screen. Host, on screen. Fs equals 0, e, street, ft dt. Camera transitions back to the host. Host, on screen. Now, let's discuss some key properties and benefits of the Laplace transform. Key properties and applications. The host discusses the properties and applications of the Laplace transform. Host, voiceover. The Laplace transform has some remarkable properties, such as linearity, time shifting, and frequency domain representation. These properties make it an invaluable tool in solving differential equations, analyzing control systems, and more. Real-world examples and diagrams illustrate applications. Host, voiceover. Whether you're dealing with circuits, mechanical systems, or signal processing, the Laplace transform provides a powerful way to simplify complex problems and find solutions. Conclusion. Host summarizes the key takeaways. Host, on screen. In conclusion, the Laplace transform is a mathematical gem that opens up new avenues for solving intricate problems in various fields. We've covered what it is, how to compute it, and some of its practical applications. Closing shot of the host in front of the whiteboard. Host, voiceover. I hope this video has shed some light on the Laplace transform and its significance. If you found this content helpful, please give it a thumbs up and subscribe for more educational videos. Outro music fades in. Host, on screen. Thank you for joining us today. And remember, mathematics is the key to understanding the world around us. Stay curious and keep exploring. Introduction. Opening shot of a chalkboard with equations written on it. Host, voiceover. Hello everyone, and welcome back to your channel name. Today, we're diving deep into the fascinating world of linear differential equations. Camera transitions to the host standing in front of a whiteboard. Host, on screen. Linear differential equations may sound intimidating, but fear not, because by the end of this video, you'll have a solid understanding of what they are and how to solve them. What is a linear differential equation? Visual aids and equations appear on the whiteboard as the host explains. Host, voiceover. So, what exactly is a linear differential equation? Well, it's an equation involving a function and its derivatives. These equations are linear because the highest power of the function and its derivatives is always 1. Camera zooms in on equations. Host, on screen. Here's a general form of a linear differential equation. Equation appears on screen. Host, voiceover. Di dx plus px, y equals qx. Host, on screen. In this equation, Y represents the function we're trying to find. Px and qx are given functions of x, and dx represents the derivative of y with respect to x. Camera transitions back to the host. Host on screen now. Let's see how we can solve these equations. Solving linear differential equations. The host explains the steps as equations, and graphs are displayed. Host, voiceover. To solve a linear differential equation, we can use an integrating factor. Here's the step-by-step process. 1. Equation with px and qx appears. Host, on screen. Start with the linear differential equation. 2. Calculation of integrating factor. Host, on screen. Calculate the integrating factor μx, using the formula μx equals e px dx. 3. Multiplying both sides by the integrating factor. Host, on screen. Multiply both sides of the equation by μx. 4. Resultant equation. Host, on screen. This simplifies the equation to μx, dx plus μx, px, y equals μx, qx. 5. Integration and final solution. Host, on screen. Now, integrate both sides to find x. Camera transitions back to the host. Host, on screen. And there you have it. That's how you solve linear differential equations. Applications. The host discusses real-world applications of linear differential equations. Host, voiceover. Linear differential equations are incredibly important in various fields, including physics, engineering, economics, and biology. They help us model and understand dynamic systems, from population growth to electrical circuits. Conclusion. Host summarizes the key points. Host, on screen. In summary, linear differential equations are a powerful tool in mathematics with wide-ranging applications. We've learned what they are, how to solve them using integrating factors, and their real-world significance. Closing shot of the host in front of the whiteboard. Host, voiceover. I hope you found this video informative and helpful. If you did, don't forget to give it a thumbs up, and subscribe for more educational content. And as always, feel free to leave your questions and suggestions in the comments below. Outro music fades in. Host on screen. Thank you for watching, and I'll see you in the next video. Until then, keep exploring the fascinating world of mathematics, unlocking the power of ordinary differential equations. Real-world applications. Opening shot. A busy city with traffic lights. Narrator, voiceover. Welcome to a journey through the fascinating world of ordinary differential equations and their real-world applications. Join us as we explore how these mathematical tools play a crucial role in solving complex problems and shaping our daily lives. Chapter 1. Understanding Odes. Narrator, voiceover. Begin with a solid understanding of what ordinary differential equations, odes, are and why they are essential in various fields. Chapter 2. Dynamics of population growth. Narrator, voiceover. Dive into the dynamics of population growth. See how odes model the growth and decline of populations in biology and ecology. Chapter 3. Electrical circuits and RC networks. Narrator, voiceover. Explore electrical circuits and RC networks. Learn how odes help analyze and design circuits in electrical engineering. Chapter 4. Vibrations and mechanical systems. Narrator, voiceover. Feel the vibrations of mechanical systems. Discover how odes describe the motion of springs, pendulums, and more. Chapter 5. Heat transfer and diffusion. Narrator, voiceover. Experience heat transfer and diffusion. See how odes govern the flow of heat in materials and the spread of substances. Chapter 6. Chemical reactions and kinetics. Narrator, voiceover. Witness chemical reactions and kinetics. Understand how odes model reaction rates and chemical processes. Chapter 7. Economics and financial models. Narrator, voiceover. Navigate economics and financial models. Explore how odes help forecast economic trends and stock market fluctuations. Chapter 8. Epidemic modeling. Narrator, voiceover. Investigate epidemic modeling. Learn how odes are used to predict and control the spread of diseases. Chapter 9. Control theory and robotics. Narrator, voiceover. Control the world of robotics. See how odes are employed in control theory to guide autonomous systems. Chapter 10. Environmental studies. Narrator, voiceover. Explore environmental studies. Discover how odes aid in environmental modeling and conservation efforts. Closing shot. A scientist analyzing data on a computer. Narrator, voiceover. Ordinary differential equations are the silent heroes behind the scenes, driving progress in science, engineering, and everyday life. Join us in our next episode as we dive even deeper into these applications and unveil their impact on our world. Evaluating Ordinary Differential Equations, a Comprehensive Guide. Opening shot. A mathematician at a chalkboard filled with differential equations. Narrator, voiceover, welcome to the world of evaluating ordinary differential equations, where mathematical elegance meets real-world problem solving. Join us on this comprehensive journey as we delve deep into the methods and techniques used to analyze and solve ODEs. Chapter 1. Review of Basics. Narrator, voiceover, start with a review of the basics. Brush up on essential mathematical concepts and terminologies related to differential equations. Chapter 2. Classification of ODEs. Narrator, voiceover, dive into the classification of ordinary differential equations. Learn how to categorize ODEs based on their order, linearity, and more. Chapter 3. Analytical methods. Narrator, voiceover, explore analytical methods for solving ODEs. Discover techniques like separation of variables, integrating factors, and exact equations. Chapter 4. Series solutions. Narrator, voiceover, delve into series solutions for ODEs. Understand how power series and Taylor series can be used to find solutions. Chapter 5. Laplace transforms. Narrator, voiceover, master Laplace transforms as a powerful tool for solving ODEs. Learn how to transform ODEs into algebraic equations. Chapter 6. Numerical methods. Narrator, voiceover, understand numerical methods for solving ODEs. Explore techniques like Euler's method, Runge-Kutta methods, and finite differences. Chapter 7. Phase plane analysis. Narrator, voiceover, navigate phase plane analysis for ODEs. Visualize solutions and equilibrium points in two-dimensional systems. Chapter 8. Stability analysis. Narrator, voiceover, investigate stability analysis for ODEs. Learn how to determine the stability of solutions and critical points. Chapter 9. Bifurcation theory. Narrator, voiceover, peek into bifurcation theory. Explore how ODE solutions can undergo qualitative changes with parameter variations. Chapter 10. Applications in science and engineering. Narrator, voiceover, see practical applications of ODEs in science and engineering. Discover how they describe dynamic systems and natural phenomena. Closing shot. A scientist working with a computer simulation. Narrator, voiceover, evaluating ordinary differential equations is a journey of mathematical exploration and problem solving. Join us in our next episode as we apply these concepts to real-world scenarios and discover their profound impact on our understanding of the world. Demystifying differential equations, an introduction. Opening shot. A mathematical formula on a chalkboard. Narrator, voiceover, welcome to the world of differential equations, where mathematics meets the real world. Join us on this journey as we introduce you to the fundamental concepts of differential equations. Chapter 1. What are differential equations? Narrator, voiceover, start with the basics. Understand what differential equations are and why they are essential in various fields of science and engineering. Chapter 2. Types of differential equations. Narrator, voiceover, dive into the different types of differential equations. Explore ordinary differential equations, ODEs, and partial differential equations, PDEs. Chapter 3. Solving first-order ODEs. Narrator, voiceover, learn how to solve first-order ordinary differential equations. Explore separation of variables, integrating factors, and exact equations. Chapter 4. Higher-order ODEs. Narrator, voiceover, delve into higher-order ordinary differential equations. See how to solve second-order and higher-order ODEs using various methods. Chapter 5. Applications in science and engineering. Narrator, voiceover, witness the applications of differential equations in science and engineering. Discover how they describe real-world phenomena. Chapter 6. Laplace transforms. Narrator, voiceover, explore Laplace transforms. Learn how this powerful tool simplifies solving differential equations in the time domain. Chapter 7. Fourier series and PDEs. Narrator, voiceover, navigate Fourier series and partial differential equations. Understand their role in solving complex problems in heat transfer, wave propagation, and more. Chapter 8. Numerical methods. Narrator, voiceover, understand numerical methods for solving differential equations. Explore techniques like Euler's method and finite differences. Chapter 9. Beyond the basics. Narrator, voiceover, peek into advanced topics in differential equations. Discover nonlinear equations, stability analysis, and chaos theory. Chapter 10. Practical applications. Narrator, voiceover, see practical applications of differential equations in fields like physics, engineering, biology, and economics. Closing shot. A scientist at a chalkboard filled with equations. Narrator, voiceover, differential equations are the language of change, describing how things evolve over time. Join us in our next episode as we dive deeper into the fascinating world of these mathematical marvels.